Welcome back, everyone, to MAE170. This is part 2 of lecture 12 in week 7. In part 1, we've covered the phase lag compensators. And in this part 2, we're going to cover some other kind of controller, which are very, very common. And they are known as proportional, integral, and derivative controllers, aka PID controllers. So PID controllers are used in closed loop systems in order to take advantage of the error by making adjustment to the plant performance using the controller itself. So why do we call these controllers proportional, integral, and derivative? Because they're going to have 3 parts, up to 3 parts: the proportional part, the integral part, and the derivative part. And all these parts are connected to the error. So what is the error for a closed loop control system? We know it very well, always in the assumption that we're considering a unity feedback loop system. The error is the input minus the output signal. So ideally, we want the error to be driven to 0, or at least less to a certain required value. This is in the time domain, but also in the Laplace domain, we can write the same. The error is always the input minus the output. And as usual, we can compute the steady state error by taking the limit for t that goes to infinity of the error function in the time domain, or in the S domain by applying the final value theorem, all things that we know. All right, so PID controllers are very commonly used because, well, they are simple, quite intuitive, and fairly easy to build. As I said, they have up to 3 parts, so that the control signal, that is the output of the control unit, the control block in the block diagram, is going to have up to 3 parts. One proportional to the error, one that is proportional to the integral of the error, and one that is proportional to the derivative of the error. So if we take a look at the block diagram of our closed loop system, we have, as usual, the input, the output, our plant G of S, and we have our controller GC. So before the controller, the signal that is the input of the controller block is the error itself. So let's see how this error is taken and converted to the control signal. The control signal is whatever comes after the control block. So that is the signal that it becomes the input of our plant. So if we zoom in the controller block, we can visualize it as the error coming in, and then it splits into 3 parts. One is going to be multiplied by a constant Kp, and then this branch is going to end up into a summing junction over here. Then we have another part, so always the error. Now we multiply by 1 over S. By multiplying a function by 1 over S, or by dividing it by S, it's like taking the integral. So we're taking the integral of the error. And then we multiply this integral by another coefficient, which we're going to call Ki. I is because of the integral. And then the result of it will also be fed into this summing junction. Finally, the third branch will be the derivative of the error. So we have to take the derivative of the error. How do we do that in the S domain? We multiply it by S. And then the result, which is the derivative of the error, will be multiplied by a constant. And now we're going to use Kd. And the result of it will also be fed into the sum injunction. Therefore, the output of the controller block is our control signal C of S, which is GC, the controller, times the error. So the transfer function, GC, it is the output over the input. What is the output relative to this block here? The output is the control signal, C of S, divided by the input, which is in this case, the error E of S. And so this is equal to Kp plus Ki over S plus Kd times S. So the three coefficients Kp, Ki, and Kd are positive real numbers. This is what it means. So the goal for designing a PID controller is to come up with the values for Kp, Ki, and Kd so that we meet the requirements for our control system, whether it is a requirement in terms of steady state error or a requirement in terms of the transient part of the response, that is percent overshoot, rise time, peak time, so on and so forth. Well, right here, I just, recalling what I've said in words, that is the derivative of the error function in the time domain is equal to S times the function itself in the S domain, whereas the integral of the error function is equal to the error function divided by S in the Laplace domain. Sometimes we don't need all three branches of the controller. And in fact, if you can do your job by using a simpler version, well, you should go for that. You don't need to always use a complete PID controller. The PID controller per se would have all three coefficients different than 0. But you can also have a PI controller in which the derivative is not taken into account. So you only have a contribution of the error itself and of the integral of the error. Or you can also have only a PD controller, proportional derivative controller. In that case, the coefficient Ki is equal to 0. We saw in the homework and in the sample midterm, you had a problem in which you had to find the values for Kp and Kd. So in other words, you were designing a PD controller. So you already know how to do that. You just have to satisfy the requirements and you come up with values of Kp and Kd. And in the midterm, you had to do the same, but now for a PI controller. So you already know how to design it without knowing that you were actually designing a proportional integral controller. I mean, I wrote it down, but maybe it wasn't really clear what the proportional part was referring to and what was the integral part referring to. Well, both of them, or even the derivative part, refer to the error, okay? So closed loop systems, and we are referring to the error. I just want to draw a parallel now between these controllers, and especially PD controller, PI, and the complete PID with what we saw last time, that is lead compensator, lag compensator, and the combination of the two, lead lag compensator. Let's start with the proportional derivative one, so the PD controller, which is Kp plus Kd times S, or we can also write it down as Kd that multiplies S plus Kp over Kd. So you see here, it's quite evident that by using this kind of controller, we are adding a real zero. So being real has to be obviously on the x-axis, and the location of this zero is minus kp over kd. Being both kp and kd positive, then minus the ratio of the two is a negative number, so we're fine. We're introducing a negative zero. Now, I want to draw the parallel between the PID controller with the lead compensator. If you recall, the lead compensator had 1, 0 at minus sigma z, but we also had one real pole. So how can we compare the two? The PID controller only has 1, 0, and the lead compensator has 1, 0, but also one pole. So you can think about the PID controller as the extreme version of the lead compensator, in which we push the real pole all the way to minus infinity. So it kind of disappears. On the other hand, we have the PI controller, or proportional integral controller, which we can write as Kp plus Ki over S. And then by manipulating it a little bit, we just have the common denominator as S. So the numerator becomes Skp plus Ki. And then we write Kp that multiplies S plus Ki over Kp over S. So this is the transfer function for a PI controller. And notice that we're adding one real zero at minus Ki over Kp, but we're also adding a pole at the origin. So a PI controller adds to the uncontrolled system both a zero, negative real zero, and a pole at the origin. Now let's draw the parallel between a PI controller and a lag compensator. A lag compensator had 1, 0 to the left of the pole. Here I'm exaggerating. I told you last time that the zero and the pole should be very close to the imaginary axis, but here I just want to draw the parallel. So you can see that we have sort of the same structure in which the real zero is to the left of the real pole. So you can think about the PI controller as the extreme case for a lag compensator, in which the pole of the compensator is pushed all the way to the origin. With the PD1, we would drag the pole all the way to minus infinity, and now we're dragging the pole all the way to the origin. And so now if we consider the overall PID controller, so we keep all three branches. We have the proportional, the integral, and the derivative one. Now I'm going to write it down in a better form so it is clear that we have a second order or second degree polynomial at the numerator. So we're going to have 2 zeros and one pole at the origin. The 2 zeros here, I already wrote them down. They are at this location. So are they real or are they complex conjugate? Well, it depends on the argument of the square root. If whatever is inside or under the square root is positive or equal to 0, then the 2 zeros that we are adding are real. Otherwise, we're adding 2 complex conjugate zeros. So let's assume that we have two real zeros. So in that case, the two zeros are right here. Let's say this is Z2 and Z1, and then we have our pole at the origin. Now let's consider what happens for a lead lag compensator. That is, we have both the pair of 0 and pole for the lead and the 0 and the pole for the lag. All right. So once again, you can draw the parallel between the PID controller and the lead lag compensator by thinking about dragging one of the poles, the lead pole to minus infinity and the lag pole to the origin. Once again, here, this comparison is valid only if Z1 and Z2 are real numbers. But in general, Z1 and Z2 can be complex conjugate, and that happens if this quantity, the argument of the square root is negative. So I just wanted to show you that, because when I told you last time that the compensators were really controllers, it's because you see mathematically they're pretty much the same. There's not much difference between a PDI controller and the phase, lead, and lag compensator. The main difference is that the lead lag compensator can only have poles and zeros that are real, whereas a PID, with a PID, you have the luxury of having the two zeros that can be complex conjugates, but at the same time, you have only one pole, and that is at the origin. So you're also, when you're using a PID controller, you're augmenting the type of the system, the type number, because you're adding one open loop pole. So if the uncontrolled system was type 0, by adding a PID controller, you would make it type 1, which can be beneficiary or might not be beneficiary. It depends on your application. Now I want to visualize the control signals, and in particular the three branches of the control signals, in relationship to the error function. So when we visualize a function, as I said many times, it is useful to visualize it in the time domain. So let's say that our error function is this blue curve over here. So now I'm focusing on the top left plot, in which we're looking at the proportional contribution of the PID controller. So E of t is our error. It's an error function that changes with time. So the proportional part of it, this reddish curve here, is going to be the error itself multiplied by Kp. And so in this case, I'm using a Kp that is greater than 1, so I'm amplifying the error function. But whenever the error function goes to 0, also the control signal, the proportional part of the control signal goes to 0. It's quite intuitive. And when we have a maximum for the error, we have also a maximum in the control part. And same thing, when we have a minimum, we also have a minimum. This is pretty intuitive. Now, when we take a look at the integral contribution, well, we still have our error function. The error function is always the same. But now you see that the integral, well, might not be very intuitive. So the integral is going to be, it starts at 0 because you can think about the integral as the area below the function E of t. So at the very beginning, at t0, there's no area. And so the contribution is 0. This green curve is the integral of e of t dt multiplied by a constant ki. Then as e of t progresses, then there's going to be some area, positive area, because we are above the x-axis. And so the contribution due to the integral is going to be positive. And then when the error function drops into negative parts, then we have to subtract a portion of the area. So the contribution to the integral part decreases until the error function is positive again. So then the contribution of the controller starts increasing again. Lastly, we have the derivative contribution. So once again, always starting with our error function. Now we have to draw the derivative, and we can also multiply this derivative, that is dE over dt, by a constant kd. So we start, for instance, in this plot, we start at t0 with a derivative equal to 0. We have a 0 derivative. So the yellow curve is going to be 0 at t equals 0. Again, this is not always the case. I'm just describing what happens for this particular plot. Then when we have the maximum negative derivative at this point right here, this corresponds to the maximum negative derivative. And we're going to have a minimum when it comes to the derivative itself, because we have the maximum negative, so in other words, a minimum right here. And then once again, looking at the e of t function, when we reach a minimum with 0 derivative, the yellow curve must pass through 0, and so on and so forth. You can visualize also the maximum positive derivative right here at this point. So you're going to have a maximum when it comes to the derivative. So it is more intuitive to look at the contributions, proportional, integral, and derivative in the time domain. However, it is easier to manipulate mathematically these quantities in the S domain, because, let me repeat it once again, in order to take the integral of a function, all you need to do in the S domain is to divide by S. And when you take a derivative of a function, all you need to do is to multiply the function by S. All right, so now I want to take a look at an example to better understand the nature of these PID controllers. This example is also quite relatable, because everyone has a car or has been in one. So our plant, what we want to control is a car, and the input is going to be the angle of the gas pedal, and the output is going to be the speed of the car, which I'm going to indicate with V, but I will also indicate it as x dot, where x is the distance that the car has covered. So you put down your foot on the gas pedal, and when you reach a certain angle, after a little bit, after the transient part, the car will reach a constant speed. So we can simplify the overall plant in order to get this intuition that at a certain angle, after a little bit, you're going to get a constant velocity with a first order system. So first order system, let's just use the simplest transfer function, 1 over s plus a. So we have one pole at minus a. So our input is going to be the gas pedal angle, and the output is going to be our car velocity, v or x dot, whichever. So as I said, let's assume that you step on the pedal and you press it down almost instantaneously to a certain angle. So you're performing a step input, step on the pedal, step input. So let's say that your step input is a certain angle, theta 0. So what is going to be the final velocity of the car, the steady state value of the velocity? Well, the output, which is, we can call it v of s, is going to be equal to the transfer function times the input. Now, since we have a step input, I'm going to use constant over s. So v of s, the velocity, is going to be our output. Now, you know very well that in order to find the steady state value, which can be applied because we have one pole at the origin and the other pole is negative. So we check the two conditions for the final value theorem to be applied. So the steady state value for the velocity is the limit for s that goes to 0 of s v of s. And so I'm going to go down here. This is equal to s times 1 over s plus a times theta 0 over s. And so your final velocity is theta 0 over a. So if we want to plot the velocity as time passes, well, the velocity, you start at 0. And let's say that automatically or almost instantaneously, the gas pedal goes to this angle, theta 0, a certain angle, then the velocity will increase, then asymptotically will reach this final value of theta 0 over a. So this is the behavior of a first order system. But this is an open loop system. We don't have any controller. This is just how the car behaves. So now we might want to design a controller if we want the car to do certain things. But before doing that, I want to modify slightly the plant. In fact, the problem is it's not very intuitive to drive by commanding a certain pedal angle. It's not that if you want to go 20 miles per hour, you say, okay, I have to press down the gas pedal at 40 degrees or 35. I don't know. You don't really do that. When you drive, you modify your speed by increasing or decreasing the gas pedal. So you're commanding really the rate of change of the angle. So in other words, your input is really theta dot, the rate of change of the angle. So it makes more sense to consider the transfer function between the real input, that is theta dot, and the velocity of the car, x dot. So we know that the plant 1 over s plus a took us from the gas pedal angle to the velocity of the car. That is still a thing, but our new input is theta dot. So how do we go from the rate of change of theta to theta itself? Well, theta dot is the derivative of theta. So if we have the derivative, if we want the angle, what do we have to do? We have to integrate. And in the S domain, the integration is simply 1 over S. So you see here in this example, I'm combining pretty much everything that we've seen so far, from block diagrams to S domain to time domain, final value theorem, intuitions, root locus, and pretty much everything. I want to give you a general idea. All right, so now that our input is indeed the rate of change of the angle of the gas pedal, our new transfer function is going to be the combination of these two blocks. So really our new transfer function is 1 over S times S plus A. So we're dealing with the second order system. All right, so this is just a modification in order to make it more intuitive, because it makes more sense to derive commanding a rate of change of the angle rather than a certain value for the angle for the gas pedal. Okay, now we're ready to introduce a controller, but which controller are we going to use? Well, it depends on our goal. So we're going to see 3 cases. I'm going to explain the first 2, and if we have time, the third one. Otherwise, I'm just going to leave it to you. But we're going to see an example of just a simple proportional controller, so proportional to the error. And our goal will be to reach and maintain a certain speed with our car. So we'll see that that can be done just using a proportional controller. We don't need to complicate things any further by using a PD or PI or PID controller. Then we're going to take a look at another example. And we want to go from a stoplight to another traffic light and stopping at the second one. And we'll see that we cannot do that by using a simple proportional controller, but we have to implement a proportional derivative controller. So these concepts of proportional derivative, or PID controllers, when you drive a car, you are the controller, so you are actually implementing these things without thinking about them. You are doing that, but here is the mathematical explanation of what you're doing, almost automatically without thinking. Finally, the third example, again, if we have time, we're going to see it. It's just the complete PID. And the goal here is to close up the gap with the car that we have in front. And we're going to see that, or it's still contained in the notes for your curiosity. If you were to use just the PD controller, you could never catch up with the car in front of you. There's always going to be a gap, and that gap is the steady state error. But let's go back to case 1. So here, once again, let's review. The goal is to reach and maintain a certain speed. So we start at 0, and we want to get to a certain speed. Let's say we want to reach the speed limit that is 25 miles per hour. And so now we close our loop. And this is our new plant with second order system. And we're adding this controller, only proportional. So we have KP. What is our input? Our input is the reference velocity, the velocity that we want to reach, in this case, 25 miles per hour, or whatever you want. And the output is going to be our actual velocity. So the error between the two, the difference between the two is going to be our error signal. The error signal is then going to be multiplied by the constant Kp, and which will change also the units. It doesn't have Kp will change units because the output of the controller is the input of our plant, and the input of our plant was the rate of change of the gas pedal. So it's pretty much, if you think about you being the controller, is the signal that goes from your brain to your leg. Say, okay, now you, based on the difference between the actual velocity I'm going at and the reference velocity, the velocity I want to go at, I'm going to press down or release the gas pedal. All right, so let's take a look at the closed loop transfer function very quickly. Here, there's nothing new, so I'm going to go a little bit fast. All right, so now we have the freedom of choosing a parameter, Kp. So you see here, we're dealing with the perfect example that we've studied, that is the root locus. We have one parameter that we can vary. So very quickly, we can draw the root locus for the system. We have the characteristic equation being 1 plus Kp times 1 over S times S plus A. Our open loop transfer function is 1 over S times S plus A. So we have one pole at the origin and one pole at minus A. So our root locus is our, usual cross. And this will extend to infinity. There we go. So depending on the value of Kp, we're going to have different behaviors of the car. Let's say that we choose a quite an aggressive controller, so big value for Kp. So with the big value for Kp, we see that the poles of the closed loop transfer function are complex conjugates. So we're going to have a quite big percent overshoot. We're going to have oscillations. So the response will look something like this. So eventually we'll oscillate our way to 25 miles per hour, but this means that we're going to exceed the speed limit and maybe go to, I don't know, 35 miles per hour first, and then we let go of the accelerator until we slow down, and maybe we reach 20 miles per hour, and then we kind of go fast and slow. It's not really the best way to get to our speed limit. It is the fastest way if you just want to get there first, but you're not going to maintain the speed limit very well. So you might want to decrease a little bit your gain. So if you are a driver that drives all the way to 40 and then slows down and then again up, then you have a high gain. So maybe you want to reduce the gain a little bit. So let's say that we reduce it a little bit, but we still have complex conjugate poles. So the response is going to be a little bit delayed, but it's still oscillate. We still have oscillations. So in order not to have oscillations, we would have to have even lower Kp, such that we have real poles. So we have an overdamped system, and therefore the response will never cross the final value, and it will just approach it asymptotically without having an overshoot. And so we're having here, we're dealing with a low Kp coefficient. So in this application, you might want to have a low Kp rather than the high Kp. So that's exactly what you want. If you don't want to get a ticket for speeding, you definitely want to have a Kp such that your closed loop poles are real and not complex conjugate. But however, if your intention is only to reach eventually, so the speed limit, so if you're only concerned about the steady state value, or in other words, if you want to drive the steady state error to 0, then all values for KP are valid because all these curves will eventually go to 25 miles per hour. So again, it depends on your goals. Now let's see case 2. And now the goal is slightly different. Instead of starting from 0 and getting to a certain velocity, we want to start from a certain position and then get to another position and stop there and get there with 0 velocity too. So in other words, you can think about going from one stoplight to another stoplight, but the second one being red. So you have to stop. So let's try to see if we can solve this problem simply using a proportional controller. Why not? We always want to use the simpler version first if it works. However, here the objective is slightly different, so we have to change our block diagram slightly, and that is because the output is not the velocity of the car anymore, but is the position of the car. So our output is X ref, so a reference position, reference to, we can say maybe the first traffic light. And sorry, the output is going to be our actual position, and the input is going to be the reference position. So here we have a position, not a velocity. So if we were dealing with 1 over s times s plus a, that was our transfer function that took theta dot and transformed it into x dot. But since we want the position, once again, having x dot, we want x, what do we need to do? We need to integrate the signal. So we need to multiply it by 1 over s. And here, why not? We can just consider this new plant, this new transfer function. It's not really a new plant, but it's new transfer function. So here we have a third order system. We have 2 poles at the origin and 1 pole at minus a. And as controller, as I said, let's try first to see if a proportional controller can work. Once again, first thing to do, let's write down the closed loop transfer function. And then the best thing that we can do, once again, is to try and draw the root locus, because we only have one parameter, kp, once again, so why not drawing the root locus? So our characteristic polynomial is the denominator of the closed loop transfer function. We have 2 poles at the origin, 1 pole at minus a. And so we have 3 asymptotes, one asymptote being the negative real axis. And the other 2 asymptotes, the other 2 branches will depart from the origin and go this way. So you see that there's a problem here. No matter the value of kp, your system is unstable, because as soon as you increase kp, as soon as kp is not 0, then your closed loop poles will be, even for very small values of kp, we have these 2 that have positive real parts. And so that leads to an unstable system. So let's say that we have an input. What is our input? Well, it's a step input, because when we start, we have to cover a constant distance. So the reference distance is constant. And as the car moves, the actual distance that is covered will increase, but the reference distance is constant. So when we have a constant function is a step function. But here it doesn't really matter because no matter the value of Kp, the system is unstable. So the response will look like this. What is the response? It's the actual position of the car. That means that we're going to reach the reference right here. And you see that the derivative of the position, which is the velocity, is positive. So pretty much we're going through the red light. And we definitely don't want to do that. So we using just a proportional controller and relating it to the car itself, then you pass the light until you stop here, and then you put into reverse until you go back, but with even higher negative speed until you go back even before where you started, and then you stop again, and these oscillations just increase in amplitude until infinity. So we have an unstable system. You definitely don't want to have a proportional controller only when you want to stop at a traffic light. Here, the idea is to increase the complexity of the controller. So we might want to have a portion of the controller that takes care also of the rate of change of the error. Because if a proportional controller only just looks at, okay, how far am I from the second stoplight? Let's say, okay, I've arrived here. There's no more error. So, okay, the control signal, if I had only a proportional controller, would be 0. So it means now I release the pedal, but you release the gas pedal, you're still going forward because of inertia. So a proportional controller cannot foresee what happens in the future. So the proportional controller, you can think about it as something that takes care of only the instantaneous part. So the instantaneous error, and that's what's the proportional part of it takes care of. The derivative part will take care of something that happens in the future. So it takes care of the rate of change of the error. So you can get to the second traffic light at 0 speed. Then you can extend this reasoning and say, okay, the integral then will take care of the past behavior of the error. In fact, the integral is just accumulates the error. Well, anyway, without further ado, let's apply a proportional derivative controller to the problem, and let's see if we can actually get to the second stoplight and stop there. So here we have Kp plus Kd times S. Now we have the derivative part of the controller applied always to our new plant, which is a third order system. So our closed loop transfer function is slightly different. And so we can rewrite the characteristic polynomial or characteristic equation as 1 plus Kd times S plus Kp over Kd over S squared times S plus A equals 0. So it's in the canonical form for the root locus. Why not? Let's also see the root locus. It's always good to draw the root locus so you can see whether or not you're dealing with the stable system or not. That's very important. All right, so in this case, we have 2 poles at the origin, as before, 1 pole at minus A. And then we have 1, 0. We can, by choosing value for Kp, over KD, by choosing that ratio, we can decide where to place the 0. Now, in order to get a stable system, this 0 must be between -a and 0. So let's choose it right here. If it was to the left of -a, we would have an unstable system, and I'll let you see that for yourselves. So just draw the root locus and you'll see that we would have an unstable system. All right, so this root locus is actually the same as we saw for an example last time. For the lag compensator, we have this kind of a circle here. There we go. So as we increase KD, we're moving away from the open loop poles at 0 or at -a, and following the branches of the root locus. So the first thing that we see is that for all values of Kp and Kd, we have a stable system, granted that the 0 again is between -a and 0. So that's good. What about the steady state error? What's a steady state error? It's the difference between the actual position at the end and the reference position. So if the steady state error is 0, it means that we are exactly at the stop sign. As I explained, the input is a step input because we have the reference distance that we have to cover is constant. So we're just going to call it x0. And since we are in the S domain, step input has to be divided by S. So the error function is the input R of S times 1 over 1 plus K times, or GC times G. So in this case, we have KP plus KDS over S squared times S plus A. Here we know that we have a stable system, so this implies that FVT, so the final value theorem, is applicable. So we can find the steady state value of the error by using the final value theorem in the S domain, which is much better, much easier. All right, so here rearranging a little bit. This goes away with this. We have S squared times S plus A times X naught over S squared times S plus A plus KP plus KDS. And so now if S goes to 0, this goes away, and this all go to 0. So great. It means that we are arriving at the second stop with the 0. We're arriving there and we are staying there. So not only are we at the second traffic light, but we're also there with the 0 velocity because this is the steady state error. Unfortunately, for this kind of plant, so for a third order system in such form, and for this PD controller, the best result that you can get when you plot the actual output, that is the distance, you'll see that you will still have a slight overshoot. And then asymptotically, you'll get to the reference point. That means that in reality, you're getting to the second stop sign, but you're overshooting a little bit, and then you have to go back, and then you kind of oscillate. So you're still overshooting a little bit. However, if your objective is just to get there with zero velocity, you can do it by just implementing a PID controller. All right, for the third case, it's the full PID controller. I'll leave it up to you to take a look at it. If you have questions, just ask me. It's still is an example like that. So the goal here is to catch up with the car in front of us, and I'll show you that. So in other words, we want the steady state error. This steady state error meaning the difference between the position of the car in front of you and you are the red car, has to be equal to zero. In order to do that, a PID controller is not possible. You must need a PID controller. Another thing that I wanted to point out, that for this case, I went back to thinking, just for sake of this example, that the controller's output is the pedal angle, it's not the pedal angle's rate of change. Anyway, it's not really important. It is just to show that using just a proportional derivative controller, just skipping through the notes, the steady state error is finite but not equal to zero. It means that you'll always be behind the green car. And in order to drive that error to zero, you would need a full PID controller. As you can see over here, the limit where s goes to zero of s times E of s is zero. All right. With that being said, now, how do we actually find the coefficients, Kp, Ki, and Kd? Well, we normally have three ways of doing so. Well, the first way, you've already seen it. We just select values based on the system requirements. So you have to come up with, by either equating coefficients of the characteristic polynomials, you just have to come up with a certain number of equations. So at least have or at most have as many equations as parameters that you want to determine. If you have fewer equations, that means that you have infinite possibilities. So you can, for instance, pick Kp, and then the equations will determine Kd and Ki. Or if you have just exactly three equations and you can solve the system, if the system has one solution, then you have one solution for Kp, one for Kd, and one for Ki. So you've already done that. We've already seen it, how to do that. And the next homework is going to be exactly that. You'll have to find the values for Ki, Kp, and Kd by satisfying requirements. So you're going to come up with certain equations. You have to solve these equations. Another option that might seem silly, but this is done, it's just to manual tune the coefficients. So you kind of go by trial and errors. Usually, they're not really blind trials, but it's really not of much interest here. It's more of an application. You should have seen that in MAE106. There are instructions, but it's usually a guess. So you maybe fix Kp first, and then start tuning Ki and then Kd. So it's a manual tuning of the coefficients based on the output until the output looks like the one that you want. A third option is to use the Ziegler-Nichols method, and it gives you some estimate. So some estimate for these coefficients. And you can see there in the table 7.5 at page 457 of your textbook. So I'll give you some guidelines on how to choose these parameters. Again, it's not phenomenally important. I just want you to know that these are the three main ways of picking the control parameters. It's more interesting, the first one, in my opinion, because you can relate actual requirements to the position of the poles, of the dominant poles on the S-plane, and then you can link that to the coefficient themselves. All right, so this is all for today, and I'll see you next time. Have a great weekend and take care.